the last thing we did was rotation of mirrors, right? So when a mirror is turned through a certain angle, then the reflected ray turns through twice the angle. Okay, so we normally do see it like, the reflection from a door or from a window. You do see a reflection, and as the door is opened or the window is opened, you will see the reflected, the image part of it is actually sweeping faster. It actually sweeps faster, and that's because the reflected ray turns through twice the angle, and I showed it to you as a proof. As if the angle turned by the mirror is theta, the reflected ray turns through 2 theta. Okay, that's the last thing. Now what we are going to do today is on spherical mirrors. So plane mirrors is the first thing that we did. Plane mirrors, normal mirrors. And all you have to do is geometrically use angle of incidence, angle of reflection, and then you can work through anything. So if an object is placed in front of a mirror, the image is supposed to be formed exactly same distance behind, right? Now if you have multiple plane mirrors, then you can get multiple images. Like for example, if you have a mirror like this and a mirror like this, and if you put an object and you're looking at it from here, how many images can you see? If you keep two plane mirrors at right angles to each other and you put something in the middle, how many images can you see? Images. Okay. What happens is when you're standing on this side, you will see an image on this side here, right? For this mirror. And this mirror will capture that image and put it up here. And you will see one more on this side. So you'll see 3 images. You can actually show it by ray diagrams. You can actually draw the ray diagrams. It will go here, bounce here, and bounces off this way. And you can see that it will form 3 images. The number of images formed, there is a certain rule that you can follow. That is 360 divided by theta minus 1. That's a formula for number of images formed. So in this case, what's the angle? 90. So what is 360 divided by 90? 4. 4 minus 1, 3. So the number of images, 3 images. Now if you make the angle like this, like 20 degrees, and if you put an object inside, so in other words, you keep 2 mirrors at 20-degree angle, and you go and stand in the middle as you're the object. And if you look around, how many images should you see? Put 20 there. So 360 divided by 20 minus 1, which is 18 minus 1, 17 images. So you can actually literally count 17 of your images. So the number of images formed from multiple mirrors is this. What if the angle, what if I have 2 plane mirrors kept an angle of 0 degree? Isn't this 0 degree? Parallel. Parallel is 0 degrees. So if the angle is 0 degrees, how many images will you see? Infinite. 360 divided by 0 is infinite, minus 1 is infinite. So you will see infinite. So if you have a plane mirror there and a plane mirror here and you stand right in the middle, you will see yourself like multiple, like infinite of them. In fact, it becomes so many of them that you hardly see your image because it is pretty far away and pretty, feeble. The image is very dim. But the number of images formed is infinite. Okay? I think if you move into some glass mirror houses and all that, house of mirrors, you will see something like that. So when mirrors are kept on either side, then you'll get confused because there are so many images. And if you have a mirror here and a mirror there and a mirror behind me, you will see a lot more. Okay, so that's about plane mirrors. We will use plane mirrors wherever. Now curved mirrors or spherical mirrors. What's a spherical mirror? It's a mirror that is formed from a part of a sphere. Okay? So what you do is you take a sphere, take a glass ball, hollow glass ball, break it. So when you break this hollow glass ball, you may get a piece like that, right? If you coat the inside of that glass ball, if you coat it the inside, the outside becomes reflecting. And if you coat the outside, the inside becomes reflecting. And so we get two kinds of mirrors. This is a convex mirror, and this is a concave mirror. Two kinds of mirrors that can be formed from a spherical shell. One is a convex mirror, and the other is a concave mirror. So if you look at a mirror, you can actually see whether it's convex or concave. Because cave, you know what a cave is, right? Caving in, cave. Look at this side. Look at the side where you're supposed to be, seeing your reflection. This side, isn't it caving in? Right? So it's caving in, so that's why concave. Vex is like bulge. So if you're looking at this reflecting surface, you can see it's bulged out. So if you look inside a spoon, what are you seeing? What kind of mirror? Concave. And outside the spoon? Convex. Okay? Just for you to quickly. Now this one, what kind of mirror is this? Convex. Because you can see that's a spherical mirror. This is the inside which is coated. Outside is shiny, just like this. Exactly like that. See? Outside is shiny because the inside is coated. So when you look from here, it's waxed, bulged. Now the same thing was that. That's that mirror. It's concave, right? Caving in. This is caving in. That's caving in. Wow. All right, we'll see more of it. Okay, so this is okay. Really. So that's a concave mirror, and the other one's a convex mirror. And what we are studying right now is more about this. Okay. So let's learn more about convex and concave mirrors and the properties and so on. So let's first go through convex mirror, concave mirror. So that's a concave mirror. For a mirror, there are some terminologies that we generally use. First is to get used to it. the center of curvature, C. What is the center of curvature? It's the center of the sphere of which this mirror is a part. Okay? So center of curvature is the center of the sphere of which the mirror is a part. That's center of curvature. And then pole of the mirror. Pole of the mirror is the geometric center of the mirror itself. So the very center of the mirror, that's called the pole of the mirror. The geometric center of the mirror, like for this mirror, it is right there, pole. It's on the mirror. This dotted line that connects the center of curvature and the pole, and it is an extended line. This is called the principal axis. Principal axis of the mirror. Okay. Now, what will happen when you shine light onto that mirror? When parallel beam of light comes and strikes the mirror, what happens? Okay. So suppose a ray goes right like this. If a ray goes from here like that along the principal axis, and if it strikes the mirror, what will happen? It will go back again along the same path. Why? Why? What angle is that? What is the angle of incidence? 0. Because at this point the normal is right there. So if a ray goes right on the normal, it will bounce back exactly, just like a mirror like this. This is the normal, right? If a ray goes through the normal, it will just bounce back along the same path because the angle of incidence is 0. Okay? Now, this ray, so if a ray goes like this, it hits and bounces back and goes again, the same way it came in. If a ray goes and hits here, like that, where's the normal? Where's the normal for this point? Is it like this?
It's going through the center.
It's going to the center. So the normal is this. And so the angle of incidence is right there. You see that? That's the angle of incidence. And so the ray will get reflected like that. So that the angle of incidence and angle of reflection are same. Now if a ray goes and hits wider, it goes through like that. If a ray goes from here, goes through here. If a ray goes through and hits there. So all these rays, these are parallel, it's a parallel beam of light. So what happens to the parallel beam of light when it comes and hits the mirror, such as the concave mirror? After reflection, they all come to one spot, and that's called the focus. So C stands for center of curvature. P stands for pole. CP, extended line CP is the principal axis. And F stands for the focus. FP is called the focal length. FP, the distance FP is called the focal length. Distance FP is called the focal length, which is from here to here. And the distance CP is called the radius of curvature. You can understand those terms right away, right? Radius of curvature means like what is the radius of this big circle or sphere. So if I'm looking at this sphere or this one, if I just imagine extending this curvature, it goes like that. So the center is possibly here. So that will be the radius of curvature. And the connection between radius of curvature and center of curvature, the focal length is radius of curvature over 2. The focal length is half of the radius of curvature. The focal length is equal to radius of curvature divided by 2. And this is only for a narrow parallel beam of light. If you take a wide beam of light, this doesn't really apply. We'll see that later. So we are talking about narrow parallel beam of light, which means I'm not talking about this wide stuff. Yes. So we are not talking about a wide beam of light like this. We are talking about a narrow beam of light. Okay? If a narrow beam of light comes and hits, it comes to the focus. There's a focal point. And that is the focal length is half the radius of curvature. So if the radius of curvature of this one is like 60 centimeters, the focal length will be, what is that?
Battery.
Of the laptop?
No, my phone.
Oh.
Or the battery.
Okay. So if the radius of curvature is 60 centimeters, the focal length will be 30. This is clear? Yeah. Question?
So like my dad has this box, like it's a cube, it's all mirrors on the inside, and like what would happen? What happens if you like put say like a candle in like say a sphere, like a mirror sphere, like a concave?
It's a complete sphere
Yeah.
with a little hole.
Well, no holes at all, and you just
You
have,
put the mirror
say if you have
in,
a
you
like
can like
candle
you cover it back up.
in a concave sphere, would it be completely dark or?
I'm not getting the picture of what you're
So
saying.
say if we have a mirror, like a sphere that's a mirror on the inside, and you have a candle in the.
So is it a complete ball?
Yeah.
Okay. How do you access inside then?
Well, let's just say you have it in there. Like say there's a lid or something.
Okay. So it's a ball. Okay, you put the candle inside.
Is it completely dark in the mirror? Or is it?
Inside?
Yes.
No, inside should be bright.
But where would the light go?
The light is just bouncing off, and then getting absorbed.
So I know it's like you're saying if it's absorbed in
No, but it's continuously being emitted, right?
correct.
So as long as the light is existing, as long as the light is present, it is actually generating electromagnetic waves. So whether it's a candle light or anything, is generating electromagnetic waves, so which is basically going to bounce back and forth continuously. But then as it bounces back and forth, it absorbs. The surface is not a complete reflector. The surface absorbs. As I said the other day, there is a proportion of reflection, the reflection coefficient, transmission coefficient, and the absorption coefficient. So there are some proportions. Now, you can't have a mirror which is like completely reflecting all the time. And so what will happen is the energy is going to be the light energy. So the light energy is going to bounce back and forth and until it's getting absorbed continuously. So, you will see the energy after some time in the form of heat on the sphere. But if the heat is dissipated to the room, then you won't notice it. It's not too much. Yeah, it is there. Yeah, it is not going to be dark. Because as long as a candle is lit or a light is on, electromagnetic waves are coming out. So when you put in fact, electromagnetic waves cannot be seen by you. Light is not something that we see. We cannot see light. We cannot see the electromagnetic waves. The only thing that we see is when those electromagnetic waves, which is light, comes and hits on a surface, that surface scatters the light. And when it scatters the light, it actually gives the what do you call definition for colors and for that object. Like you're wearing a different shirt, green shirt, white tee, and all that. So when light bounces from the white tee, all the colors of the electromagnetic spectrum bounces off, so it comes out as white. When it goes and hits the green shirt, what it does is it takes all the wavelengths of light into it, but reflects only that of green. So the green color is only coming to your eyes, and so it looks green. Okay? Black, all the colors go in there, and they all get absorbed, nothing comes out, so it becomes black. So that's how we get the definition of an object. We cannot see those lights. Yeah.
So, is that why the image in that mirror comes upside down, because the bottom rays go to the top?
We will see that in detail very soon. Okay? So you will see that in detail. But what are the characteristics of this focus? The characteristics of this focus is it's a real focus. Why do I call it real focus? Because the rays are actually coming and hitting there, right? These are actually coming and see, these are all rays that are actually coming and converging to that spot. So it is a real focus. You should be able to see that real focus. If light is focused with this mirror, you should be able to see it. Now, this is not a parallel beam of light. This is not a parallel beam of light, but still you can actually see it gets focused. Somewhere there, see? You can see the light getting focused. So what's happening is it's going to hit here and it throws it there. Now, if it is a parallel beam of light, you will see the focus very clearly. Like if it is sunny outside, sunlight is nearly parallel, right? Sunlight is nearly parallel because it's coming from far away. It's nearly parallel. If you take this outside in this and face it to the sun, what happens is the sunlight comes and hits here and they converge to that spot. And that spot can be really, really concentrated in energy, that it can actually burn stuff. So if you go take this to this, face it to the sunlight and take a piece of paper and just place it where you think the focus is. If you place it exactly at the focus, the paper will burn because all this energy is concentrated at one little spot. Okay, that's only if it is perfectly parallel beam of light, and you have to get that exact spot. So people in the past, they used concave mirrors to burn objects like ships and stuff like that. It's a kind of a weapon. They just took it close enough, shot the sunlight onto the ship or boat or whatever, and they kept putting it right at the focus, and the ignition temperature is reached, and then it catches fire. Yeah, fires can come in like that. All right, so it's a real focus. Now you will see why I'm concentrating on this thing. So which one has a real focus? A concave mirror has a real focus. Remember that. And this is the concave mirror. The picturization of the mirror should always be there. Don't just forget the fact that concave is caving in, that type. And the first one which I did for you is concave. So you can see that it's a real one. Now, looking to the convex mirror. A convex mirror. So that's a convex mirror. The same definitions go here also. This is the pole of the mirror. That's the center of curvature of the mirror. And obviously nothing's going to happen, no activity is going to be seen from this side, right? Because that's a coated side. Reflection is going to be on this side only. Reflections, if at all there is any, this side. So if you have a light ray going like this, what will happen to that light ray? Bounce right back. Now what will happen to a light ray that goes and hits there? It kind of bounces that way. Where's the normal? Normal, it's the line that kind of connects it. That's a normal. Okay. So this is a normal. So you can see the angle of incidence right there. So the reflected ray is going to go like this. The reflected ray goes like that. What if there's a light ray going and hitting here? Same thing applies. The reflected ray appears to be going like that. What if there's a light ray going and hitting here? The reflected ray appears to be going like this. If a light ray goes and hits here, the reflected ray appears to be going this way. So the reflected ray is kind of diverging. See, this is diverging. What was the previous one? Converging. Yeah. In the previous one, in concave, the parallel beam of light converged to a certain spot. In this case, the beam of light, the same parallel beam of light, after bouncing, is diverging. It's getting scattered away. But they're all appearing to diverge from a certain spot. Can you see that spot? These are all appearing to diverge from a spot. And that spot is the focus. Sometimes they call it principal focus. It's the same thing. So that's the focus of the mirror, of the concave mirror, convex mirror. The same definitions go. This is the focal length. That's the radius of curvature. All those definitions stay the same. Principal axis, everything stays the same. The only difference is, yeah, the rule for focal length is the same. What kind of a focus is this? Virtual, imaginary. So this is a virtual focus. So a convex mirror has a virtual focus. Now you have to be very careful with this term virtual and real, because when we solve problems with mirrors, we will need to put sign conventions. Right? We will need to put some, just like in equations of motion we put sign conventions, right? Forward positive, backward negative, same way. In optics, the book uses a different kind of sign convention, and therefore they use different equations for mirrors, lenses, and all that. We are going to use only one equation mainly for all of them. But we have to stick to sign conventions. What's the convention that we're going to stick to? Anything real is positive. Anything virtual is negative. That's what we're going to take. That's when we solve problems. So when we solve problems, I'll be stressing on that more. So why do we have to know that a convex mirror has a virtual focus? Because the focal length is negative. Okay, so you have to be careful about that. Oh, it's a convex mirror. I have to put F as negative. Okay. So before you put anything down, think of it. Oh, is it real or virtual? Is it real or virtual? And then once you put all those things there, you should be able to get it. Now let's see how images are formed by mirrors. How the images are formed by mirrors. Okay. Let's take a concave mirror first. That's a principal axis. Now, to know where the image is formed, we need to draw ray diagrams, right? Because wave diagrams are really messy. Ray diagrams are better, much better, easier. So when you draw ray diagrams, like how many rays should you draw to get an image? Like I think I showed you with the plane mirror. How many rays did we use to actually pinpoint the image position? Two. All you need is 2 rays coming from the object. Image will be identified, right? You need 2 rays. Now, what are the different rays that we can draw? Here they are. Now, here's the focus. Here's the center of curvature. This is something that we always mark for mirrors. As soon as you draw the mirror, you'll say, all right, here's the focus, here's the center of curvature. Now, if a ray goes through the center of curvature, if it goes through the center of curvature, what will happen to that ray after hitting the mirror? It will come back along the same path. See? Goes back. That's one of them. So the first ray that you can draw probably is a ray through C will just bounce back. That's one possible ray. Another ray you can draw is this. A ray that's going through the focus after hitting the mirror. What should happen to it? It will be rendered parallel. That is the second ray. It's a possible ray. So a ray through F will be rendered parallel to principal axis. So a ray going through the focus will be rendered parallel to the principal axis. The third ray that you can possibly draw is a ray that's going so that's the first ray, that's the second ray. The third ray is a ray that goes parallel to the principal axis. After hitting the mirror, what will happen? It will go through the focus. So that's the third one, a ray parallel to principal axis will reflect and go through focus. These are 3 possible rays that we can draw to get the image. Okay? Now, if you look back into the plane mirrors, I put a little extended object, right? Now the extended object was an arrow. What we did was we took 2 rays from the tip of from the head of the arrow to pinpoint where the image is, and we took 2 rays from the tail of the arrow to find out where the image was, right? Can you look back into the previous picture for the plane mirrors? For the extended object, to pinpoint the image position of the head of the arrow, I took 2 rays from there and made it bounce. To find out where the tail's image is formed, I took 2 rays from there and bounced it. That's pretty much what we are supposed to be doing. Alright, so this is a mirror, and that's a principal axis, and that's a focus, and that's a center of curvature. If an object is far away on the principal axis, far away, so that's an object. If an object is far away from the principal axis, so the object is like far away, how do you get the image? So here's the arrow. I need 2 rays to come from here, right? And 2 rays to come from the bottom. But in this particular situation, you don't require to draw 2 rays from here. The reason is this: if you can find out where the head of the arrow is located, the tail of the arrow is going to be on the principal axis. So it will be on the principal axis, so you don't have to really worry about it. So for example, if the image of this object is here, where is the tail? Right there. It should be on the axis. Because the tail is on the axis, you don't have to draw that part of it. So basically you need only 2 rays. Here's the first ray. What happens to this ray? A ray that goes parallel to the principal axis after hitting the mirror should go where? Through the focus. So it goes right through the focus. You need 1 more ray. Which ray can you draw? One through the focus. Okay. So if you take 1 through the focus, what will happen to that ray? It will go parallel. Where do these 2 rays meet? Those 2 rays after reflection, where do they meet? Right? So this is the place where the image of that arrowhead is formed. The image of this is right there. So the head of the arrow is right there. Where's the tail? So the image is here. That's the image. It's pretty easy to draw and find out where the image is formed. All you need is 2 rays. Any of those 2 rays which I said. Okay? You don't have to draw all the 3. Just 2 of those are enough. So this is the image formed. Now what is the basic idea of this? Object placed far beyond C. Object placed far beyond C. Not beyond C. The singer beyond C. Object placed far beyond C. What kind of image is formed? Characteristics. Inverted. It's called inverted. So we get an inverted image. What else do you see?
Small.
Diminished. Now, is it real or virtual? Real. It's a real image. And the other thing you can say is it's between C and F. So the image is formed between C and F. So it's an inverted image. It's a diminished image. It's a real image. And it's between C and F. Now, can you see this one, inverted and real? These two go together. If it's an inverted image, it has to be real. Okay? If it's an upright image, it has to be virtual. It has to be. So they go together. So if you're told that an inverted image is formed, you know that it is a real image. If you're told an upright image is formed, that means you know it is a virtual image. Make sense? When you stand in front of a plane mirror, what do you see? Inverted or upright? Upright. So what kind of image is that? Virtual. So remember, these go together. If it is an inverted image, it is a real image. If it is an upright image, it is a virtual image. In all cases. Whether you're talking about lenses or mirrors, any kind of mirror, always true. Inverted will be real. Upright will be virtual. Yeah.
I'm so confused what you mean by really. So it can be like cast on the screen.
I can get this on a screen.
Okay.
I should be able to get this on a screen. Right now you saw this. See, that the light source over there is the object. Okay? Now where's the center of curvature of this supposed to be? This focus is somewhere here. Center of curvature is somewhere here. Okay? Center is here and the focus is here. So if I take that as the object, isn't it beyond C? And if it is beyond C, I should be able to get the image on a screen. I'm able to get the image on the screen, which means it's a real image. Now if it was bright outside, we could also demonstrate something. Let me show that. Yeah, when you say real, it is something that can be captured on a screen. So that's why it's called a real image. Now, if it's a virtual image, you can see it, but you cannot capture it. Okay, this is your first picture. So, what does this say? When the object is far away, image is formed where? It's between the center of curvature and the focus. And what kind of image is expected to be formed? It's an inverted image. It's real, therefore. And it is smaller, diminished. Now if I bring the object closer and closer and closer and bring it all the way here. So if I bring the object closer and closer and reach here so far, where is the image formed? So what's happening here? A ray that goes parallel goes through the focus. And a ray that goes through the focus will go parallel. You see it? A ray that goes through the focus will go parallel. A ray that goes parallel will go through the focus. And where is the image formed? Right there. And what kind of image is that? What kind of image is that? Inverted, the same as before. And therefore it's real. Say I'm putting in one line now. Since it is inverted, I'm putting it in real. Then what do you have? Same size. It will form the same size image. So when the object is kept at C, the image is formed at C. Image is formed exactly at C. To know where the center of curvature of this one is, what you have to do is this: keep an object in front of it and move it. Move it till center of curvature is so far away. All right, here's the image. Keep the object. Are you able to see the image? You can just stand up, then you can see. Do you see an inverted image of the marker?
Yeah.
And is it the same size?
Yes.
If it is the same size, then it will be at the center of curvature. Now, if I do this, what kind of size is that?
Small.
And that's the first picture that we drew, right? The image is smaller. You see it? You see that?
Yeah.
Yeah? Its image is smaller. Now, if I take it closer and closer, now the image is kind of getting big. But if I take it to exactly a certain spot, right there, You can see the image is exactly same size. So this is the center of curvature, which is almost my expectation there. Okay? So center of curvature is a point where you can get the same sized image. So what I was doing was I was holding the marker like this, and I'm seeing an inverted image of the same marker like that. And by moving it back and forth, I can actually locate the point where I get exactly the same size of the marker's image font. And once I get that, I can locate that place as the center of curvature. If I know that that is the center of curvature, where's the focus? Focus must be exactly halfway down. So these are the characteristics. Now what will happen if we I move the object closer here? Let me put the object here. If I put the object closer, so object between C and F. If the object is between C and F, how is the ray diagram going to be formed? Watch. A ray that goes parallel will go through the focus. What's the other ray that you can draw? A ray that goes through the focus will be rendered parallel. So a ray that goes to the focus will be rendered parallel. Where's the image formed? Right there. What are the characteristics of the image? Inverted, real, and
Figure size.
magnified. We use the term magnified. Right, Ben? So you get an inverted image, you get a real image, and magnified image. Draw all those things, then you'll be fine. Inverted image, real image, magnified, and beyond C. The image is formed beyond C. Now what we're going to do next is take this and put it right on the focus. And we'll see what happens. Done? When the object is placed on the focus, then what happens? So object at F. See what happens to the image. A ray that goes like that will go through the focus. Now, you don't have any other option here other than imagining a ray going like this. So imagine the concave mirror goes all the way there. What will happen to that ray? After hitting, what will happen to that ray? Bounce straight back and goes like that. Where do these meet? At infinity. So, when the object is at F, you cannot form an image because they don't converge at all. They just go parallel. So when the object is at F, image at infinity. So it can't be captured on a screen because it's far away. It's supposed to be at infinity. So they don't converge. Okay? So when the object is at F, image is at infinity. That means if I put my hand exactly at the focus, I won't be able to see my hand because the image is supposed to be something like that there. The image is supposed to be at infinity, so I won't get any focused image. Now what will happen if you move it further inside? If you move the object here, that's focus. We moved it little inside. So if that's a focus, we put the object inside the focus. Now the ray diagrams go like this. So object within the focal distance. Okay, the focal distance is from here to here. So we're putting it within the focal distance. Now what will happen? A ray that goes parallel will go through the focus. That's the first ray. And the other ray is a ray that goes from here and hits the mirror like this. What will happen to that? A ray that goes and hits the mirror like that will get bounced back, and there it goes. Do these meet here? No. What kind of rays are these? Diverging rays, correct? Diverging rays appears, so these rays appear to be coming from this point. These are rays. Now if you look at these rays are appearing to come from there. It's only an appearance. So where is the image formed? Right there. So what kind of image is that? What kind of image is that? Virtual. That's why it's upright. It's a virtual image, and you can see it's an upright image. And it's magnified. It's highly magnified. And it is behind the mirror. The image is behind the mirror. Now, where are these applied? Where do you apply this kind of mirror? Any place where this is applied? You know, the first images that we saw, they are applied in certain optical instruments. They are definitely used. Like if you want to make an image upside down, then you can use a concave mirror and make it, just flip the image. Sometimes, when you're trying to look at something using an object, using an optical instrument, the image will come out upside down. Now, if you know that the image is coming upside down, you want to flip it, use a concave mirror, and put the object at the center of curvature. It will just flip the image for you. Okay. Now, where is this one used? Microscope normally uses mirror lenses. We'll get to that one. Huh? Dentist, correct. The dentist uses this mirror. So what he does, it's a small mirror, it's not as big as this. What he does is, this is the tooth that he wants to examine. So he puts the mirror in such a way that the tooth comes within the focal length. And what he is looking at from here is a huge image of the tooth, exactly upright, the same way as he's not seeing an inverted image. He's seeing it the same way and magnified. And also from the other side. You see, if there's a tooth like this, open the mouth, the tooth is here. If there is something on this side, he won't be able to see otherwise, right? But if he puts a mirror like that, he's able to see from the other side. So a dentist uses this mirror regularly. This is also what we call as a shaving mirror. Do you have one at home like this? A shaving mirror? You get it for $5 or $2. If you go to a dollar shop, you'll get these mirrors, shaving mirrors. Now, why these are called shaving mirrors is you just keep your face within the focal distance and see for yourself.
Yeah.
You'll see a lot more detail than what you normally see in mirror. Right?
Yeah.
Let me see that distance. Oh, that distance. So even after a nice shave, you still will see a lot of difference. You see?
Yeah, I see.
Oh, yeah, close this. What do you know about a concave mirror now? It has a real focus, number one, and images. When you keep the object very far away, the image is formed between center and F. If you put the object at C, the image is formed same size. If you put the object within F and C, the image is thrown far away and inverted. Right? It's magnified, it's inverted. If you put the object at F, no image. If you put the object within F and within the focal distance, the image formed is totally different from the other ones. It is upright, it is virtual, and it is highly magnified. Okay? So you saw all those ray diagrams. You should keep them all like in your mind. There's only one ray diagram for the other mirror. There's only one ray diagram for this mirror. Wherever you keep the object, it's going to form same kind of image. So that's the principal axis. So if I put the object here, if I put the object there, let's mark the focus, let's mark the center of curvature. So this is a convex mirror. Looking for rays now. The first ray, a ray that goes parallel to the principal axis. What happens to it after reflection? It bounces off in such a way that it goes away from the focus. And you need one more ray, and that's the ray that we're going to take is the ray that is heading towards the center of curvature. A ray that's heading towards the center of curvature. What will happen to that ray? It will bounce straight back and it will go on. So when you look at this object from here, where is the image formed? Where the two dotted lines meet. In other words, where do these reflected rays appear to come from? From there. So the image is there. What are the characteristics of the image? Is upright. What does it mean? It's virtual. And then it's diminished. And it's behind the mirror. And that is what a convex mirror produces. You can be wherever you are. Wherever you are, you're going to see a smaller of you, right? You will see a small image of you, and you are upright, which means you're virtual. Okay, so your virtual image is what you see from there, diminished, and the image is formed here. It's formed right there, or almost right there, almost where I'm pointing. That's exactly the place where the image is formed, wherever you look from. Okay, so wherever, that's why it doesn't matter where. Even if I keep this here, you can see I'm close to this mirror, but still the marker is smaller than this, right? And where is the marker image formed? Almost like right there. So The image formed by a convex mirror is always going to be virtual, upright, and diminished. Where do they use this? Where is this mirror used? Rear view mirrors in your cars, or blind spot mirrors, like you're coming from here and you want to take a turn, but there's something that's blocking the view, but this mirror will actually tell you there's something. Okay, so that's a blind spot mirror, and mainly the rear view mirror. What's the purpose of using it for the rear view mirror? Is because you can see everything behind you, right? You can see a lot more than what a plane mirror can show. But the only thing is, it is small. It is diminished. All right. We'll continue this.